8.5. In 8.5, we're still doing testing, so guess what? We still do step 1, step 2, step 3, step 4, step 5. The thing that has changed is now we're testing 2 populations instead of 1, and we are only looking at independent samples. So let me show you again what is the same, what is different. Now, sigma is known, so right there I know I'm going to calculate a z-value and I'm going to use the z-table. So that's very important right there. Now, let me show you a slight difference in step 1. We still have the null and the alternate. We still have equals. We still have less than, greater than, or not equal to. But here's the difference. You'll never have any numerical values when you're comparing 2 populations, because what you're doing is you're comparing population 1 to population 2. So the null will always be that population 1 is equal to population 2. The alternate will be population 1 and 2 being compared. So population 1 is either less than, greater than, or not equal to population 2. Now, the test statistic, now that we have 2 samples, this formula changes. It's x bar 1 minus x bar 2, and then in the denominator you have this. Now, it looks a little complicated, but again, I'm going to show you how to put it into your calculator, and it is not hard to find. Now, step 3 is the same, the p-value, so the z-table. So this tells me then, if my alternate is a less than, then I just use the number from the table. If it's a greater than, I do 1 minus the number from the table, and then if it is not equal to, then I have to find 2 probabilities and add them like we did previously. Now, step 4 and step 5 are exactly the same. If the p-value is less than or equal to alpha, you reject. When you reject, you have sufficient evidence. When the p-value is greater than alpha, you fail to reject, which means you have insufficient. These 2 steps are the same all through Chapter 8. Those comparisons never change. So the easiest thing to do is to look at an example from the book. So look on page 484. I'm getting there myself. And we are doing number 15. And it reads, REM, or rapid eye movement sleep, is sleep during which most dreams occur. So each night a person has both REM and non-REM sleep. However, it is thought that children have more than adults. So assume that it's normally distributed. So we're going to say mu1, population 1, is from the children. They tell us the sample size is 10. They tell us that this sample's average is 2.8 hours. And they tell us that sigma is 0.5. So when sigma is known, we know our test statistic will be a z-value. Then the problem goes on to tell us about the second set, which is our adults. They also did a random sample of 10. It tells us that their average is 2.1 hours from this sample, and it is given that sigma is 0.7. So I put all the information given from the book here. Now we're going to set up the null and the alternate. So before I even read the problem, I know that I'm going to say mu1 is equal to mu2. Because when you're comparing 2 different populations, you will not ever have numerical values here. This is saying the children and the adults experience the same average REM sleep. But then it reads, do these data indicate that on average the children, and children is mu1, tend to have more than adults? So in this case, mu1 is children, more than would be greater than the adults. So we have a greater than. Well, since sigma is known, I know I have a greater than, which tells me I have a right-tailed test. All right, then in step 2, what we're going to do is calculate our z-value, and all the values we use are up here. So my z-value is x bar 1, 2.8, minus x bar 2, 2.1, divided by the square root of, sigma 1, 0.5 squared divided by n1, 10, plus sigma 2, 0.7 squared divided by n2, 10. Now, the key here is when you put this into your calculator, you're going to enclose the numerator in parentheses. Then you're going to push divided by. You're going to open this radical or this square root. There'll be a parenthesis to start it. You do not use another parenthesis until the end, and then you will push equals. So let me see if I can show you this on the calculator. I know it's not always the greatest because of the glare, so I'm going to do the best that I can. Trying to hold this is quite comical for me. Okay. Clear that out. All right, so the numerator in parentheses, 2.8 minus 2.1, close parentheses. Then I'm going to use the division. Then I need to open my radical, which is second x squared, and my radical opens. My calculator automatically puts a parenthesis there. So that's the only parenthesis until I enter everything that goes under the radical. So now I'm going to put 0.5 raised to the second power divided by 10 plus 0.7 squared divided by 10. Now I'm going to close the parenthesis and then push equals. And I get 2.57 and so forth. So that is 2.57. So Z is equal to 2.57. Now, since we have a right-tailed, okay, then that means when we calculate the probability, we're going to find the probability that Z is greater than, because the alternate was a greater than, and we calculated this test statistic to be 2.57. Well, since we have a greater than, we know we're going to do 1 minus the number from the table. So we're going to go to the table and we're going to find 2.57 on the Z table, and you should find 0.9949. So 1 minus 0.9949 is 0.0051. So now what we're going to do is compare our p-value to alpha. The p-value is 0.0051, which would be 0.51%. And we're going to compare that to alpha, and the book tells us to use alpha of 0.01, which would be 1. And 0.51% is less than 1%. So since it's less than, that tells me we will reject the null hypothesis. Well, the conclusion is when you reject that there is sufficient evidence at the 1% level of significance to conclude the alternate. And the alternate was that children have more, because greater than, to conclude the children have more REM sleep than adults. So that is how you deal with two populations when sigma is known. Now, the other scenario that can occur is still two populations, but this time sigma is unknown. So that means we're going to calculate a t-value and use the student's t-distribution. Now, if you'll notice, step 1 is exactly the same as what we just talked about in the last example. The difference is step 2 and 3, because now your test statistic is t because you have s instead of sigma. And so the p-value, you're going to use the student's t-table. Now remember, when we use the t-table, we have to find a df. Well, the df is n minus 1, and we have 2 sample sizes. Well, if your sample sizes happen to be different, then choose the smaller and take that -1. And then again, step 4 and step 5, no changes. Exactly the same as we've done all through chapter 8. So let's look at an example where sigma is unknown, so you can see what that looks like. So if you will turn, let's see, what page? 486, problem number 21. In the journal Mental Retardation, an article reported the result of a peer tutoring program to help mentally retarded children learn to read. In the experiment, the children were randomly divided into 2 groups. One they called the experimental group, so if you'll notice I have that here, and the other one they called the control group. Now if you'll notice, N1 and N2 is both 30. So in this case, then my DF will not be difficult because they had the same sample size. But again, if your sample sizes are different, always choose the smaller -1. So then as you go through, it tells us the values for each of these. So the experimental group had X bar 1 of 344.5, and notice though it gives me S. So that tells me I'm going to have to use the student's t-distribution. And then for the control group, they had a sample average of 354.2, and the standard deviation, sample standard deviation, was 50.9. Now, I know that the null will be that they scored the same on the test, both groups. It's equal. So then I'm going to read the last sentence, and it says, use 5% level of significance to test the hypothesis that there was no difference. So that would tell me mu1 is not equal to mu2. And since the alternate is not equal to, then I know that I am going to use a two-tail area on the student's t-distribution. So then I'm going to go to step 2, and because sigma is unknown, we have a sample statistic of S, I'm going to calculate a t-value. Now, it's still X bar 1, 344.5 minus 354.2, and the denominator is the square root of S1, 49.1 squared divided by N1 of 30, plus S2, 50.9 squared divided by N2, which is 30 as well. So I'm going to put all of that into my calculator, and again, just be very aware of where you put your parentheses in your calculator, and then you will calculate negative 0.75. So negative 0.75 is my test statistic. Now, when we go to the student's t-distribution, step 3, remember there are no negative values. So just for using the table, I'm going to look for 0.75. I need the DF, which is n minus 1. Both of my n's were the same size, so 30 minus 1 is 29. So we are going to look for 29. And we are looking for 0.75. So here's 29 is actually on the table, and we have a two-tail area, sorry, and I'm looking for 0.75. Well, it's very easy. It's in between the first two numbers. So I'm going to travel up between these first two numbers to the two-tail area, and I get 0.5 and 0.25. So my p-value is between 0.25 and 0.5. So now we are going to compare the p-value, which is between 0.25 and 0.5, to alpha, which they told us to use 5% or 0.05. Now I didn't draw a number line here because 0.25 is like 25%. 0.5 is like 50%. Both of those numbers are significantly larger than 0.05 or 5%. So that one's pretty easy to see. So since it is greater than, I fail to reject the null, which means I can't say anything has changed. So we have insufficient evidence to prove anything. So I have insufficient evidence at the 5% level of significance to conclude the average score for the control and experimental results are different. So basically, I haven't proven anything. And that concludes 8.5.